Welcome to this video where I wanted to have a look at a specific type of planet known as ice giants. Now we have ice giants in our solar system, but we can also have them around other stars, so exoplanets basically. So this is applicable to all sorts of planets around different sorts of stars basically. Now in our own solar system, we've got the gas giants, and these are our outer planets, but there are a subcategory of that which are classified as our ice giants, and these are Uranus and Neptune. So Jupiter and Saturn are more like the classical gas giants. These are big, large planets, predominantly gas. And then you have Uranus and Neptune. Again, they're quite large planets, they're giant planets, but they are not the traditional ones like Jupiter and Saturn, and they are classified really as ice giants. And part of the reason for that is they're cooler, they're further away from the sun. So you're typically going to find ice giants are not going to be close to their star. They're going to be quite a long way off, and they're going to be quite cool. In comparison, Jupiter and Saturn are closer, so they are going to naturally be warmer. So size comparison, basically, just to get started. So Jupiter and Saturn are relatively similar sort of size. Saturn is a little bit smaller in radius, but Uranus and Neptune are almost a third in radius in size. So these are almost a third the actual physical radius of Jupiter, so a bit smaller. Mass-wise, it's Saturn that's actually about a third of the mass of Jupiter, so quite a bit less massive. And this will make a little bit more sense when we look at the density, because Saturn's density is actually very low, despite it being not that much smaller than Jupiter. But Uranus and Neptune, they are approximately 5% the mass of Jupiter. These are a lot less massive than Jupiter. So Saturn and Jupiter, relatively close really, I suppose, but the other two are a lot less massive and a lot smaller basically. Now, the ice giants typically going to have a higher density than your more traditional gas giant. So Saturn, for example, is actually a very low density planet. And if you were to put it into water, if you could have a bath big enough and put Saturn into it, it would actually float. Its density is lower than water, so it would actually float in water. But your gas giants, your Uranus, your Neptune, these have slightly higher densities than your main gas giants. The Jupiter is actually fairly close to Uranus, but it's because they have a slightly different, well, not slightly different, they do have quite a different composition of what they're actually made of. Instead of just gases like hydrogen and helium, they have the heavier elements in there, which makes their densities a bit higher. So what basically is an ice giant then? We know they're going to be quite cool, but these are giant planets. Again, these are bigger than your terrestrial planets, and these are a few times bigger than what the Earth would be basically. And we will classify them as Newtonian size or Neptunian size, I should say. And these are comprised of elements heavier than hydrogen and helium, which would be like oxygen, your carbon, nitrogen, sulphur, those sorts of things. Anything heavier than your hydrogen and helium will typically make up your ice giant. Now, when we're talking about ice in the context of ice giants and I suppose in the context of astronomy, you're referring to volatile chemical compounds with freezing points that are greater than 100 Kelvin. So this would be like water, which is 273, ammonia and methane. These will all freeze above that temperature. That's what we would classify as a volatile chemical. Just means that it's fairly easy to vaporize or become a gas, basically. So, in contrast, the gas giants, Jupiter, Saturn, these are actually a similar composition to the Sun. They're predominantly hydrogen and helium with other elements in there as well, but the bulk of what they're made of throughout their entire structure and internally as well is mostly hydrogen and helium, which is in contrast basically to your ice giants. Now, if we have a look at the structure of Uranus and Neptune, only a small amount really is hydrogen and helium, and that's in their outer atmosphere really, or their atmosphere in general. Now, the mantle is made kind of a water ammonia sort of mix, and they supposedly have a solid core as well. And I say supposedly, we actually haven't studied these planets as well as Jupiter and Saturn. So with Jupiter and Saturn, we've had spacecraft orbiting around them, and you can get a better idea for their internal structure by how the spacecrafts move, and if the gravitational field changes slightly, you can actually work out exactly what the internal structure is like. But with Uranus and Neptune, we haven't done that. They're a bit further away, harder to get to. We haven't had spacecraft there. So a lot of this is mostly looking at models and stuff like that, as opposed to experimental work done with spacecraft. Now, the mantle, as I said, is a mix of water and ammonia, but it could be ionic or superionic water. And what that basically means is because you've got the really high pressures there, it starts to behave a little bit different. And when this happens, the oxygen in the water then crystallizes, but the hydrogen ions still float around freely within this oxygen lattice. And because you've got this freely moving hydrogen ions, it makes it almost as conductive as a normal metal. So you get this quite conductive, almost like ocean of this super ionic water, really, midway through, which is kind of the mantle. So you get some really interesting behavior here. But again, this is thought to exist. It's not known to exist because, again, we haven't gone there, we've not tested it exactly, and we just don't have the spacecraft there at the moment. Maybe this will be proven wrong in the future. We don't know. But in contrast to Jupiter and Saturn, they don't have this super ionic water or ocean in their mantle, but what they do have is they have liquid and metallic hydrogen instead. So the outer parts are more molecular hydrogen, but as you get the higher pressures and temperatures and things like that, the hydrogen starts to behave differently. You get liquid hydrogen and metallic hydrogen, which again becomes very conductive, and it is responsible for some of the very large, or the largest magnetic field of planets, I suppose, in the solar system, taking out the sun. So Jupiter has an enormous magnetic field, and that's mostly down to its internal structure and having this metallic hydrogen kind of in its center. Now, the ice giants lack a solid surface, so they're not like the terrestrial planets where you can walk around on them, apart from maybe that solid core, but that's not really a surface, that's right in the center. So they are predominantly gases and liquids. So despite being called an ice giant, they're not a solid ice object. But the reason why they might be called that is that those individual compounds that now make up the planet, as it was forming in the circumstellar disk, as it was accreting, then those individual components would have been solid to start with before they actually became part of the planet. So the original starting point of the water, for example, because it's far enough away from the sun, would have been ice. And when it became part of the planet, not so much. So it's no longer really solid because you've now got a large structure that has a lot of gravitational force there, which means you've got additional heat as well. So it's no longer that solid, but that's where it would have come from, basically. So thank you for watching, and if you enjoy, then check out some of the other videos.